we're talking about satellite payloads, satellite communication payloads. I want to complement what Pavani explained to you about payloads and explain to you a bit the details of satellite payloads and communication satellite payloads. You probably still know me from last time, a few weeks ago. I didn't change things, so I'm still Joel. I'm working for SAS and SAS Engineering as on system architecture and innovation. So we're currently working as SAS 17 and needs to be Empower. I did electrical engineering background, so a bit like you, and I'm not so young anymore as well. And yeah, so that's my background. So I'm currently working on a new NGO on SAS 17 and so let's talk about payload basics. Payload, what is it that we talk about when we talk about satellite payloads? Pavani gave you already some basics, and please interrupt me if you hear something interesting, you want me to dig a bit more details into some aspects. And I want to go relatively briefly about the basics of payloads and then dig a bit more into a few interesting topics about what new novel satellite payloads bring and what interesting technical topics and new high throughput satellite and novel payload aspects. So a payload, basically, you have to think about it as a flying signal repeater, and that's actually what it is, because using satellites for communication purposes, their mission is to relay signals, to bring a signal from a point A on the Earth to another point B, also on the Earth. And so the satellite is actually a flying repeater. And in fact, the early ideas, the paper that actually brought satellite communication, that was the founding paper of satellite communication by Wells, and of 16 was calling it a repeater, a satellite communication repeater. So it means that we receive a signal and we transmit a signal, and the reception of the signal is all about receiving the signal with the highest possible quality in the band, in the reception band, then conditioning it and basically filtering it, receiving it, converting it, multiplexing it, amplification, and then retransmitting it. So all of this, depending on which frequency band we're using. Typically, the historic frequency band in satellite communication has always been C-band, so that's 3 gigahertz to 6 gigahertz. And those are the satellite systems that you can see, the old ones with the really big antennas, they used C-band. That was the first frequency band that was used afterwards. Today, we're using Ku band, which is the band that we're using also for DTH, for satellite TV. That's between 11 and 14 gigahertz, so 11, 12 gigahertz from space to Earth, and 13, 14 gigahertz from Earth to space. And today, what is today used a lot for internet over satellite is Ka band, so that's the frequency band around 20 gigahertz and 30 gigahertz, and it provides a lot more bandwidth and is more suitable for small antennas and internet via satellite. And then typically the bandwidths which were used traditionally were between 26 and 72 megahertz, and then the amplification here is in the orders of 60 to 150 watts. Okay, and then different scoping sizes. So this payload, we can normally talk about an input section and an output section. So the input section is everything that deals with receiving the signal and conditioning it, and the output section is everything that deals with high power amplification. And it really makes a big difference. When you build a satellite, you have these two sections at different parts of the satellite, because this section is about receiving signals. It needs to be in a cold place on the satellite, because the receiving devices, they work best when they're cold. And here you use, the signals are amplified a lot, so there is a significant difference between the signals here and here. A huge difference, because here they are amplified by the traveling wave tube amplifiers, and there's a lot of power transmitted here. So the output section is all about dissipating power on board of the spacecraft and making sure that you have no losses, and then retransmitting the signal. The input section first has to receive the signal with the highest possible discrimination, and what we use there right after the antennas, and we're later going to talk a bit more about the antennas, are filters. And there the filters, the signals are in C-band, Ku-band, or Ka-band. So at these frequencies, the filters are waveguide filters or coaxial filters with cavities, and each of the cavities have the electric elements. So normally between 8 and 12 of these elements. And here the signal goes through the filters like that. There you have 3 input filters. Each one of those filters filters one of those bands that we were mentioning, 26 megahertz, or 54 megahertz, or 72 megahertz, and then they select specifically one part of the signal that is uplinked for a later amplification stage. So it eliminates undesired signals, it eliminates interference, and the input section filters is all about making sure that we have very little losses in that filter, and that it is nice flat. So an important specification here would be that this part here is very flat, and also this here is as flat as possible, and that we avoid as much as possible these distortions there. So that the signal part here, this is 36 megahertz filter. Here you have here the band which can be selected and received, and if the signal would be wider, it gets more and more distorted by the fact that at the filter frequency edges, this is what we call a group delay, and it's basically that the delay through the filter depends on the frequency, and it gets distorted, and here if the signal bandwidth is wider, there we have more distortions at the edges, which can be compensated, but it's something that would need to be pre-compensated around the Earth. So and then after that we have a filtered signal that gets channeled through the satellite. So there are coaxial cables and signal passes that bring the signals through the satellite until we reach the amplification stage. And in the amplification stage, did you talk about the traveling wave tube amplifier?
I just mentioned the
okay.
it does. What I thought was more the
Okay. So the traveling wave tube amplifier is still used today a lot on satellites, and in the future it will eventually progressively be replaced, but it is still an extremely attractive piece of technology which is still used today. And it's relatively old technology, but it gets more, the recent versions are more and more efficient and still used a lot. And the reason why they're still used a lot is because of their high efficiency. They are very efficient in the sense that the DC power that we need to put into the traveling wave tubes gets converted into real output power with a very high degree of efficiency, much higher than in semiconductor amplifiers, for example. And the way they work is that you have an electron beam like on the old televisions. So I'm not sure if you're old enough to know, so the old televisions, the really big TV sets, they also had an electron beam that was scanning through the TV on a phosphor plate. And this is a bit the same thing. You have an electron beam here that gets accelerated, and there is a magnetic field, and the magnetic field keeps it really straight. So the electrons get accelerated very, very fast here. And then the RF signal is routed through waveguides with cavities along the electric beam, and then there's an interaction that happens between the blue RF signal that comes from the input of the satellite and the electron beam, and they the electron beam actually amplifies the RF signal, and here it comes out with a significant amount of amplification. And so these amplifiers exist at very high power amplifiers, so 150 watts or 160 watts, so that's really a lot, much more than you would have on semiconductors. And they are widely used today on satellites, these amplifiers, because of their efficiency. Initially, they were, in the early days, in the 90s, so they were not so reliable, so they regularly failed in orbit. But the state of the art today is that they can be built with a really, really high degree of reliability, and we have very, very rare failures. So they normally last 15 years in orbit. Then the input signal gets amplified, and we have something that characterizes this amplifier that's called an AM to AM and an AM to PM conversion. And it means that the input signal, depending on the amplitude of the input signal, we have a certain amplitude and phase on the output signal. And the desired region here really is the region where it's nice, flat. We don't want the signal to be distorted. And if we get into a region where the amplifier saturates, so that's a saturation here, it means basically that the input signal is not that the output signal is not identical to the input signal, but it gets distorted. So it gets saturated. It's like a sinus which gets cut off or which gets distorted. So the output signal is not an exact replica of the input signal, and that is an undesired behavior. So this behavior is the desired behavior, where we have a flat phase and linear AM to AM and AM to PM conversion. So these amplifiers are built so that here we have a region that is quite flat, and we can avoid this region here, which is an undesired region. And then the transponders normally are operated in a mode that we either keep the output power fixed, which is then a mode which is automatic gain control, by basically configuring the satellite so that we have a fixed point here, and we maintain this point regardless of the input power. So there is a control mechanism on the satellite that keeps this point fixed. That's called the automatic gain control or automatic link control, ARC, automatic link control. And then we can basically program the satellite so that we work at a specific point here. Or if we work in the fixed gain mode, it means that if this input signal is very weak, then we have also a low output signal, and if the input signal is amplified, we travel along this line and we have a higher output signal also.
Is this, I mean, I'm not sure, but I think when we were discussing, maybe my understanding is wrong, but we understood the fixed gain mode is you want to have a fixed output. Is that not the case?
No, it's called fixed gain because, in fact, it's the other way around. And maybe the term fixed makes it, it's a bit confusing because of the term fixed, but in fact it's the other way around. And it's called fixed gain because if the output signal varies with the input signal, then the relationship between the output and the input signal, which is the gain, is fixed. So that's why it's the other way around. But there are the two modes. After the amplifier, we have a lot of power, and you should really compare what an output filter looks like compared to an input filter. An input filter compared to this here is relatively small, and it's built with coaxial cables on board of the satellite. And here we cannot use coaxial cables anymore because the power is so high. There's no coaxial cable that could actually be used. There's no adequate technology that would have low enough losses. And the waveguides here are all painted in black, so to help power dissipation. And these filters are also a different technology. They have different cavities. They don't have the electrics anymore inside of the cavities. It's just geometry. And normally they are silver plated inside, so because silver is the best conductor with the highest, and then they are painted in black. And normally underneath there is heat dissipators, because there's so much heat produced here just by the few tens of watts which are dissipated with all of the waveguides and filters that produces so much heat on the satellite, which cannot be evacuated via convection, because in space there is no convection, there is no air, and so it needs to be radiated. And then the heat pipes transport all of the heat on the sides of the satellite, and then the heat is radiated. But the output filters are much more substantial pieces of hardware than the input filters, just because of the fact that they are much more high power. Yes, please.
So the black paint is increasing the dissipation of radiation, or?
Yes. Okay. That's why they painted in black. Then you have its reference.
When we are trying to minimize the losses, we try to constrain the conversion to heat energy, right? That is the main loss. Is heat the main loss that we are experiencing here?
Yes. So the filter, the signal here comes from the amplifier that we showed earlier. So you have these traveling wave tube amplifiers, and the output of those go inside here, and then here the main design goal is to minimize the insertion loss. So really have the smallest possible insertion loss, because all of the insertion loss is dissipated heat. So these are really the main conventional components of conventional payloads. In addition to the antennas, I will talk about antennas just later. And these are really the most important pieces of the traditional satellite.
In the new satellites, it's more electronic, or?
Sorry?
In new satellites, what's the design of, for example, or is there more become electronic phones, or?
In the new satellites, there is more electronics, yes, and we will talk about that a bit later. But the satellites are still used as a repeater today. There are novel concepts of trying to regenerate signals on board of the satellite, but in fact the amount of signal power that is, the amount of signal bandwidth that is required to be processed on the satellite is so big that even if we do processing on the satellite, it requires a lot of power. And so the most effective use of power in space is to just amplify the signal and bring it back on Earth. And even on the modern satellites with more electronic, it doesn't change. The principle doesn't change. It's still a repeater. But there's much more electronic on board of the satellite. When we design a satellite link, a satellite communication link, it's all about making choices. And we do something that we call a link budget. I don't know if you talked about link budgets. And making link budgets, it's all about making link budgets. It's a bit like the work of an accountant, but there are a lot of similarities, but also slight differences in the way the choices are made. It's about making choices of coverage, power and bandwidth, terminal choices, choices of antenna sizes, and how we allocate resources around the coverage. And normally we can trade one thing for another. So like in a budget, if you have larger antenna sizes, you can do certain things that you can't do if you have smaller antenna sizes. If you have large coverages, you dissipate your power over a large area, then you cannot have so much throughput on one point than if you have more targeted link budgets. So we try to understand a bit the details of that, and it's not the purpose here to go into the details of the equations, but I want to explain the principles. So we always have an uplink and a downlink, and we want to communicate from one point on the Earth to another point, and we need to make the assessment about what is the signal quality that we can expect at the receiver in order to evaluate how much throughput we can convey from this antenna to that antenna. And the measure of that is the signal-to-noise ratio, and it's C over N. So the signal-to-noise ratio gives us a measure of the signal quality. And making the link budget is always about computing the signal quality, computing the measure, the signal quality of reception. And in order to do that, we need to take into account the uplink power, which is measured in gain and power. We will talk about that shortly. So we have always the same components. So uplink, signal-to-noise ratio, and downlink, signal-to-noise ratio. We have power, transmitted power here, and gain, which is something that we call ERP. So it's equivalent aerated power. So it's the product of gain and power on the uplink towards the direction of the satellite. And we always have a measure of the quality of the reception, which is the satellite receiver gain over temperature. So the receiver can receive a certain signal with a certain gain in an environment where we have noise, and the noise is expressed in a certain temperature. And this always leads to a certain budget of signal-to-noise ratio, which we have on the uplink and the downlink, and the combination of all of those factors leads towards an overall signal quality that allows us to evaluate how much throughput we can achieve on the link. Have you seen in another presentation details of the link budgets? No?
Yes. Yes.
Okay. Okay. So the important thing to remember is that you can trade certain things against each other. For example, on the uplink, you can trade the power for the gain, because they are directly related. So if you have a larger dish, you need actually less power on a larger dish to achieve the same signal quality. The same is also true at the reception. So if you have a larger antenna or more gain towards a certain direction, you need less power because the antenna amplifies the signal. The free space loss is always comparable for a certain frequency. So for KU band, we always have around 260 dB free space loss, and it's always in that order of magnitude. So we can make choices on power and antenna sizes. We can also make choices on coverage area. That's pretty much it. And these factors, they add up, but they add up in a manner which is a bit different from accounting and finance, because they add up in a manner that basically you have a dominant part. So if you have a very, very small dish and a very big, if you have on one side an extremely big dish, on the one side an extremely small dish, and the small dish generates a bad signal-to-noise ratio, there is little benefit in increasing that even more. So if, for example, if you have here a link with a small antenna like 50 centimeter, and you have here a gateway like the one we have in Bedstove of 12 meter antennas, the reception quality of the TV signals will not improve if we change in Bedstove our 12 meter antennas for 20 meter antennas. It will not improve. And because the noise that the users see when they watch TV is the noise from their small dish, because the dish is so small and the gain is so little, that this part of the link, well, in that case it would obviously be the other way around, but then this part of the link to the small dish would dominate so much that it doesn't make any big difference if in Bedstove we change our 12 meter for a 20 meter And that is expressed by this formula, where the inverse is added up. And so the inverse of the uplink and the downlink are added up. And if there are other terms, they would be added up in the same manner. So if there would be adjacent satellite interference, it would add up. If there would be adjacent channel interference from other signals on the same satellite, it would add up. If we have interference from the other polarization, it adds up, and so on. And it's normally one of the terms dominates. So for example, if we watch TV over satellite and we have this small dish and we receive the signal, it's normally the fact that the small dish is so small that the noise from the small dish dominates. So that's why the interference doesn't matter so much. And the fact that we have 12-meter antenna in Batstov also doesn't matter so much. So you have a dominant factor. And then what does this C/N allow us to do? It allows us to get on scale a relationship to how much throughput we can achieve. So we have here this C/N value that we have from the link budget, and the output of the link budget allows us to put it on scale here in this relationship and achieve something that we call bits per second per hertz. So it's basically throughput. So for example, if we have a link budget that tells us we have a link quality that we can measure of 10 dB, C/N in total, then we know, okay, for 10 dB, we can achieve about 3 bits per second per hertz, which means that we take the channel bandwidth of, for example, the bandwidth we had before of 26 megahertz or 72 megahertz, and you would multiply that with the efficiency, and then you know that is the capacity of my channel. Inside of a transponder of 50 megahertz, I can transmit 150 megabit. So it's a pretty important assessment, because I know, okay, I can transmit 150 megabit if my link quality allows me to get to 10 dB signal-to-noise ratio. And if I want to increase that, I could increase parts of my link, and I would better increase the part of the link that allows me to impact the dominant factor, because in my equation there is this one dominant factor, and it's there where I need to make changes in order to improve the bit rate. So if I have, for example, 150 megabit in 50 megahertz transponder towards a dish of 50 centimeters, then it's the dish size that I need to change in order to increase the capacity of that link. And this, when we have then this transponder and we transmit signals and we achieve the signal-to-noise ratio, there is actually an optimal setting we can achieve. There is this dominant factor, and depending on the backoff I was mentioning earlier on the transponder where it saturates, there is an optimal setting for each transponder to adjust in order to get the best possible signal-to-noise ratio, so the best possible C/N signal. And here you have a measurement actually on Astra 28.2 of an 8 PSK signal, so it's 8 parts. And a perfect signal would be a point, and the fact that you have all of these points here distributed is because there is noise and interference. And if it's too cloudy and we can't make any distinction anymore, then the signal-to-noise ratio is too bad. And then we would need to change to another modulation. That's basically the principle. And the important thing is that there is an optimal setting in terms of backoff. If we increase the backoff, or if we increase the backoff, we improve the intermodulation, but the output power also decreases. So there are contradictory effects. So here, if I go back to the transfer curve, here, it's in yellow. Here, this curve. In this region here, I have very little distortion, so I have very little interference coming from distortion. So here the signal gets distorted, and then these clouds get more noisy because of the fact that the points get distorted. But the output power is also lower, so there are contradictory effects. So the C over N on the downlink decreases, but the distortion improves, and that's why we have an optimal setting. And this optimal setting can be seen here, and it's always dependent on which modulation we're using. So here in APSK we have one optimal setting here, so you have here downlink C over N, and uplink C over N and intermodulation, and here the intermodulation would be so bad that the signal is completely distorted. That's when we would not want to operate here. We also don't want to operate here because that would be too much backoff, so we would want to set the transponder as close as possible to that point. So it's really the art of configuring the satellite correctly is setting the transponders as close as possible to that point where you have the optimum balance between noise and interference, and you use the power of the satellite as optimally as possible. Any questions?
Are you using different modulation in this case to just to improve this level of this signal noise? I mean, this case is a modulation that improves this.
Yes. So this this optimal point here, this curve here depends on the modulation.
Yeah.
You would have one curve like this for one type of modulation. And if now I change the modulation, I would have, for example, another modulation, QPSK, which only has 4 points.
Yes.
Then this curve here would be different. You know how it would be different? Because if it's QPSK, the signal is less sensitive because the points are further away, so it's less sensitive to intermodulation. So then you would use less backoff, and you would basically shift the curve more towards that part where you use less backoff. And if we use a modulation which is more sensitive, like 16 APSK with a lot of points, and they are relatively close to each other, you want to avoid the intermodulation more.
Mm-hmm.
So we use more backoff, and in that case the curve shifts more in that.
Okay.
And that's always for one signal per transponder. And in fact, on the transponders today, it's quite common that we use actually more than one signal per transponder. It becomes more and more common that traditionally also for TV, there was always just one signal. So you have here the frequency band of 26 megahertz, 36 megahertz, 54 megahertz, and 72 megahertz. And you have then one signal inside which fits well inside of that transponder. That was the traditional way of using the satellites. And today, it's very common that because of different applications and different requirements, it's much more common that we use more signals per transponder. Yes?
What would be the advantage of using APSK instead of QPSK?
I will get to that. Actually, I will get to that here. So here, it's a good question. So in APSK, you have this effect that here you have a measure here, energy per bit over noise, which is similar or comparable to C over N. It's just another metric, but very similar. And here you have bits per symbol, which is also very comparable to bits per hertz. There's like subtleties, but it's the fact that if you use QPSK and only 4 points in the constellation, then you reach a point where you can actually per symbol not do more than 2 bits, because you have 2 bits per, you have 4 points, and 4 points means 2 bits, so you cannot code more. The coding of bits to symbols is limited to 2, and with APSK it's limited to 3, and with 16 APSK it's limited to 4, and so on. And so there is some advantage of using APSK because it allows you to get towards a region where you have higher spectral efficiencies.
So with one symbol you can just transmit more data at the same time?
Yes.
Okay.
With one symbol you transmit more data. It's basically as if you use the same piece of paper, but you write smaller.
Yeah.
So you have still the same size of paper, but you write smaller. And then actually, so I don't want to spend much more time because otherwise we cannot go to the other topics. But in fact, there are the usage of the modulation type QPSK, APSK, or 16 QAM or 16 APSK is an important choice, and it's a variable choice today. If you look at the scale here this curve here is very important. The red curve here is the standard we use today almost for all our communication links. Is DVB S2X, which is a really big range from -10 to actually here 21 dB silver N reference, and all of these points are different settings of modulation and coding. So each one of these points are possible configurations, and today the communication systems are such that they can automatically adjust. So for example, if we have a link budget of 10, the system automatically measures that and it adjusts to the optimal setting here. It will then choose one of those modulation and coding settings. And here we have more the QPSK, here we have APSK, then 16 APSK, 32 APSK, 64 and 256 APSK. And it's a continuous scale, and depending on where you are on this scale here, it automatically adjusts. So it's like an automatic gearing that adjusts to the appropriate modulation and coding setting. And that is really the state of the art today. So I basically touched on that. So let me get to the antennas. The antennas are really one of the key points where we can influence the link budget. The free space loss is always the same; it's physics, and on the satellite we have choices that we can make by design, but it always depends on how we use them operationally. But the antenna sizes and the powers are the key aspects that are what we can influence by design. And parabolic antennas are a key part of the satellite communication system. So here you have apparently the really big one. And the important principles to understand is that the gain multiplies with the power. You can exchange one for the other. The important metric on the transmit side is equivalent isotropic radiated power, the ERP, which is the multiplication of the gain and the power. I'll try to avoid equations, but the important thing of the gain is that it's proportional to the diameter squared. So it really is directly linked to the diameter of the antenna. And then on the receive side, it's the gain compared to the noise temperature, which is of relevance. So the noise temperature is basically what in wireless communication is the principle of physics. It's really temperature is the physical cause of noise, and if you have receivers that are cooled, they really have low noise. So you can impact noise by changing the temperature on the receiver. There are actually antenna systems that have low noise blocks that are cooled, so that they are cooled to something very close to the absolute zero, and then this measure improves. It gets better. Yes.
Is it they use liquid nitrogen?
Sorry?
Do they use liquid nitrogen?
Yes, there are antenna systems, and there are, for example, research projects also that exist an antenna systems where the receiver amplifier is cooled with liquid nitrogen or so, and it's brought very close to the absolute zero of minus 272 degrees Celsius, so close to 0 Kelvin, and then this figure improves. It gets better. Because this temperature here is the temperature of, actually really the real temperature of the atmosphere and the Earth, and actually space, because space also has, and then received by the antenna, plus the temperature of the receiver. And if you improve the temperature of the receiver, the figure improves significantly. So that's why, and because of that relationship, that's why also on the satellite you have these different panels, and you have this input section, output section, and on the satellite the satellite is built like like a tower. You have these panels on the side with the radiating elements. So you have the silver-plated panels on the side. Maybe you have seen some pictures of satellites where it looks like a silver-plated thing. Then that is actually the silver, or the reflectors are the reflecting material, or the mirror material is to radiate to space the heat, and so all of these high power amplifiers, they're on the side, and all of the equipment that is used to receive the signal, which is actually should not be heated, so you need to separate those. So those are put on the plates in between, so that you have a section on the satellite which is cool as possible, and a section on the satellite which is hot. And then the antennas on the satellite, they are parabolic antennas. They work really like parabolic antennas, and the important part there is that traditionally they are shaped reflectors, and the new design that is currently used for high throughput satellites is a different one. It's a perfect parabola, and I will talk about that later. But in fact, the principle of a shaped reflector is really, I believe, interesting. So a parabolic reflector works in a way that you have a focus point where all the signal energy comes together, and the parabola is a mathematical form which has the property that here all of the rays are parallel, so that's why the parabolic shape, because it has this focus point, the parabolic shape is used. And it can be different sections of the parabolic shape. It can be this section, or it can be also an offset section of the parabolic shape. Or it can also be a Cassegrain parabolic shape where it's reflected twice, and then the focus point is here. But on the satellite, in fact, the parabolic shape is not perfect, and sometimes it's really even visible. So this is a real picture, and this one is not broken. And the fact that the parabolic shape can be changed allows the energy to be focused in an area that is shaped on the ground. So, for example, if you have coverage areas that follow the shape of the countries of Europe, like on our Astro satellites, we normally follow the countries' shapes. The antennas are on the spacecraft. They are designed like that to have an energy distribution pattern that is exactly like the shape of Europe, there are certain things which are possible, others less, and it depends on the wavelengths. And designing that, normally that is what we do at SES with the satellite manufacturers. So the satellite manufacturers, they make exercises to show us what is possible in order to make these shapes, and then afterwards they need to build it and build these reflectors. And that's the traditional way of making satellite coverages with shaped reflectors. But as soon as they are shaped, we cannot change them anymore. And then if they're installed in space, and we have a broadcast beam that has the shape of Europe, then that's it. We live with it for 15 years. But yeah, that's typically the technology used for broadcast, parabolic antennas on board of the spacecraft. But and we mentioned during the previous lecture that we have this traditional business which is broadcast, and you broadcast one TV signal to a large area. But if we actually want to use the spacecraft to do internet access, then every individual normally has its own preferences what he wants to watch on the internet. So it's more point-to-point communication. It's more it's not a broadcasting, and then we want to optimize the satellite capacity in a different manner, and we want to make spot beams in order to allow the reuse of frequency and maximize the capacity. So that's the principle of high throughput satellites. And in order to produce this shape of coverage, the satellite antenna is different. Then normally a perfect parabola is used. So this is a perfect section of a parabolic antenna. And then an array of feeds are used. So many feeds inside of the array are used, each one to create a different spot. And there are different technologies to create these arrays, so to produce each one of these spots. But each one of the beams is a different path inside of the satellite where a certain portion of the frequency can be reused. And for these antennas, they are actually called array-fed reflector antennas. Yes, and there are different technologies and ways to build them on a satellite. And all of the high throughput satellites today, they have some form of these type of antennas in order to reuse frequency.
I may just bring it to your notice that we have past time and we have another class which starts at 5, but it's in a different building.
Okay, so you tell me that I have until 5.
That depends on the class.
Oh, okay, so Bhavani, I have until when? Until 4.
So ideally, you pass the limit, I guess. Pass the time.
Yeah.
Otherwise, you want to come to a logical conclusion somehow.
Okay, I come to a quick conclusion. Give me 10 minutes, okay? So in order to create these spot beams, there are different technologies that can be used on board of the satellite. Normally the design of this antenna requires different choices in terms of how the feeds are built. So you can, in order to have a quality signal, normally you would want to have a large feed, but the large feed would need to be, you would need to have sufficient space for the large feed. So there are technologies that allow you to combine several small feeds into one large feed. So this would be one beam, then this here would be one beam, and one of the feeds is actually used between the two beams. That's basically a multi-feed per beam type of antenna on board of the satellite. So there are different technologies that can be used, and on board of the satellite you probably have seen these satellites with the antenna with the reflectors on the side. Depending on whether you use a single feed per beam or a multi-feed per beam, you have different arrangements. You have either a transmit and receive antenna for certain parts of the beams on the ground, and then we separate them between antenna 1 and antenna 2, and then 3 and 4. Or if you use multi-feed per beam, then you have normally one big receive antenna with all of the receive feeds, one transmit antenna, and one for the gateways. And here you would basically have the pattern on the ground interlaced. So every second feed, for example, could be from this antenna, and every second beam could be from one antenna, and every other beam from the other antenna. And they would basically be make this beam pattern on the ground. So in the future, what was mentioned earlier on is basically, is there more electronics on the satellite in the future? And then the answer is yes, there is more electronics. And what we want to achieve with this additional electronics is basically flexibility. In these high throughput satellites, increase the amount of allocating the resources where it's really needed, so increase the flexibility and allocate the power and bandwidth per user, per beam over time in a flexible manner instead of having it allocated in a fixed manner. And in order to achieve that, part of the input section is then replaced with a signal processing part where we have an analog to digital conversion and a digital to analog conversion, and the signal processing allows us then to channelize and configure the signals where they are needed in such a way that if they are coming from a certain beam, if they go through the channelizer, we can rearrange them on the beam on the output so that we can reconfigure the signals where they're needed. The challenge of these processors is that the amount of bandwidth we need to process on board of the satellite is really large. So we have, for example, in Ka band, we normally have 2.5 gigahertz on 2 polarizations, so 5 gigahertz, multiplied by all the amount of beams that we have. For example, on SA-17 we have 170 beams, and the capacity of the satellite is hundreds of gigahertz, and processing hundreds of gigahertz is really significant task, and you need a lot of processing power to process that much, and the power on board of the satellite is being limited. The real driver here is the electronics that allows us to process the bits per second with as little energy as possible. So today, when we compare the processors on board of the satellite, it's about how many joules you need in order to process bits per second on board of the satellite. And just want to, and this really becomes the important metric, and that's also why today DTPs are used, so digital transparent processors, which means that the signal is just channelized and regrouped so that we can reprogram the satellite in space. We can reprogram the route and the channelization in space, but we don't demodulate in space because the demodulation would require much more power. So if we would want to basically, for example, build a router in space, so a Cisco router in space, it would require a lot of energy. So if you would, for example, one of your Cisco routers, if you would want to route hundreds of gigabit or several hundreds of gigabit, it requires much more power than we actually have in space. So that's why there is a clear benefit in avoiding to decode the signal in space and to use the satellite, to continue to use the satellite as a repeater because of the power efficiency. The processing in space adds additional distortions. So there is an additional noise term that is added in space, and that's basically quantization noise and clipping effects, which come on top of the intermodulation and interference that we already have today. And these effects come because we are transforming the analog signal into a digital signal, and that increases the potential source of noise. So depending on the load of the analog to digital converter, there is something that's called the noise power ratio. So if the signal is very weak, it is almost comparable to a bit, and then the quantization noise plays a role. And if it becomes a very large signal, then you have clipping effects, because if you have a certain bit range, and for example your bits go only to 255, but if your signal is much higher, then at some point you would need to saturate, or you would need to clip, and that's the clipping noise, and the signal will also be distorted. So there is again an optimization where in this range the signal is received with the optimal setting. And this actually is a problem for using digital devices in space, because the analog devices we use today, they have a much higher dynamic range. So this is a limited dynamic range, and that is a problem that we need to have. And in order to improve these technologies, and today we are in the process of bringing into use now the first fully digital payloads with SES-17 and mPOWER, and we have already today DTPs flying on SES-12, 14, and 15, but because they use so much energy, they only process a certain part of the bandwidth, and they only use to resolve certain connectivity problems, because the technology up to now was not such that we could process the entire payload. Only SES-17 that is being constructed now is the first one that has a fully digitized payload, so where the entire signal is digitized. And that is basically the main driver that allows us to do that is the advances of the semiconductors. So the technologies that are used in the semiconductors allow us to reduce this joule per bit per second to a point where it becomes power efficient to actually digitize in space. And today, for example, on SES-17, then it would be a technology below 32 nanometers, and today the state of the art today is around 22, 24 nanometers. And in fact, it's always lagging behind a bit from what is possible on the terrestrial side, because if you look at the latest iPhones 11 or so, it probably has, I don't know, 10 nanometer technologies, something like that. So normally the technology on the ground is one step ahead of what we can use in space, because you would need additional qualification levels. So yes, so this is really at what we have today. This is the state of the art of the high throughput satellites, fully digitized payloads. What we will do next is the beamforming is really a key aspect that will come with the next generation of payloads, where the antennas can be used to direct the beams wherever needed, with feeds that can impact, that can change the amplitude and phase to do beamforming in space. And that is only possible also if we use solid-state power amplifiers. So we mentioned that the traveling wave tube amplifiers are so efficient, but if we use solid-state power amplifiers, we have other advantages, because we can they are much smaller, and they can be used in an antenna design where we use many more, and so we can basically build antennas that direct power where needed, like on 5G, massive MIMO, like in MIMO manner, where you direct the beam where needs. So it's an electronically steerable antenna. You can build an electronically steerable antenna with this. And then the next frequency bands, I mentioned it during my last lecture, the QED bands, which are the bands at 50 gigahertz and 60 gigahertz, which allow us to increase the bandwidth of the high throughput satellites even more. And then what ESA is currently researching is optical links, and I think there are already experimental optical links working, but for high throughput satellites, it's the throughput basically that would need to be achievable with optical links in the future as well. Okay, so I understand that you need to go to another lecture, but if you have any more comments, let me know. If you have any questions.
Does the inclusion of these electronics reduce the weight of the satellite?
The electronics reduces the weight of the satellite a bit, yes. Yeah, it does. It does allow to reduce the weight of the satellite compared to the amount of bandwidth we can process. Yes, that's true. Yeah. Questions? Okay, So you have 10 minutes to go to your
Yes.
It's okay. Thank you.
Thank you very much.
Thank you.
Still need to return my email. So I will now return it and then afterwards
We did that. Yeah, we did that. We corrected it, but the way it's written,
The way it's written,
it's
something
not
like
there.
this. Yeah, it's not only written also our colleges. Exactly. And that was the problem because the chart it was not properly.
Yeah, we did it.
We did it. We did it very good. Yeah.
I didn't know you said.
Just drink water.
Yes.
I only drink water.
It's winter. Oh, it's like a big classroom.
For us, it's not problem to put out of the result.
We've done both of them.
Yeah, yeah, because we don't know what to do.
Yeah, but what's
Yeah.
required should be
Yeah,
here,
we are
so.
not sure about the result. What we are
This is what we did,
do.
only matches the draft, only change the draft. Yeah, because I'm only doing one each, and I did the plot, and you ignore the rest.
You have right. We put both. And then we choose one,
Okay,
which
then
is correct.
I'll send you the other.
Yeah, exactly.
Because our last class, I think that's I'm about to.
Okay, that is to confirm, even I'm not very sure, I have to check. Because I think we may have some projects or presentation, but not exam per se. I will not be able to check.
We don't have this. I don't remember. Because I saw on the timetable that Simos, I think, put on Saturday's
Yeah.
Moodle, that we can do our presentation and 9 of December.
There are 2 days, everyone.
Yeah, it was 2 days. So, and also for informatics, we don't have any exams.
Informatics, I don't know how, but I think it's going to be a problem.
later.
Yeah, from today it starts.
Yeah, because they changed the time zone and it's cold suddenly, you know. Maybe not the zone, sorry.
Maybe they changed also the climate.
They changed the time by 1 hour to realize.
Yeah, from
Oh. Oh no. No,
you didn't
Now
compare
you
with the
understand.
China. No, we have the 7 hours.
You didn't realize that I
Yes.
changed that time.
Yes. I didn't realize.
Okay.
So we sleep.
1 hour.
Yeah, you slept 1 hour extra, you know.
Oh, okay.
For me, what happened is that I wake up like clockwork always at the same time, even without my alarm. But then when I woke up this year, I saw the time is different.
And when we leave home, it's already not dark. Oh, that's good. But it's just for a few weeks.
Yeah.
Later it will be different.
But this is still manageable. This is not so cold yet.
No, it's good.
Hey, this is
Tomorrow I have to wear warmer clothes.
And further, I need to calculate 7 hours. So, yeah.
Is it normally 8? Or is it normally 6? Yeah. It's normally 7 hours?
Summer was 6.
Okay.
And the winter was 7.
Okay.
I don't like it.
Yeah, I know. It's hard.
Hard
Then
to
you
catch the time.
to meet to talk to your family.
Yes, if I go to family and do some work,
Oh,
we don't need to come in. You just need to catch them the time. Because they are earlier. Then they earlier than me. 7 hours, not 6 hours.
Yeah. Yeah, I know. Because it's 6 hours to the States. And actually, my boyfriend, where he is, 9 hours.
9 hours.
9. Now it's 8, but then it'll go to 9 again. So that's really hard.
Their time is earlier than
Earlier,
here.
yeah, he's earlier. So I stay up late.
Yes. When you wake up and maybe they are in the afternoon or in the
Yeah,
evening.
I talk to him in the afternoon. His afternoon. My night,
Yes.
midnight is 3 o'clock
Yes.
for him. I think I'm too old.